In discrete mathematics, relations and functions are three interconnected concepts that form the backbone of many areas in computer science. In this video, I will also explain the calculation each of topics stated in my poster. What is a relation? We define a binary relation on a set S as simply a subset of the Cartesian product S cross S. That means we take any set of ordered pairs where both the first and second elements come from set S. If the pair XY belongs to the relation, we say X is related to Y and write it as X R Y. As for the example, let set S containing 1, 2, 3, 4. I am going to define a relation R on the set SR 1, 2, 1, 3, 2, 4, 3, 3. Notice that we also have 3, 3, which means 3 is related to itself. This is called a self loop and it is perfectly allowed in relations. The Cartesian product S cross S contains all possible pairs. There are 16 of them. Our relation R has just 4 pairs. But are those 4 pairs actually inside S cross S? Let's check one by one. 1, 2, both are in S. Same goes to 1, 3, 2, 4, and 3, 3, both in S also. Since every single pair in our relation belongs to S cross S, we have proven that R is a subset of S cross S. Therefore, R is a valid binary relation on set S. Move on to the definition of a function. A function is a special type of mapping from one set called the domain to another set called range. We write this as function f maps domain D to range R. The rule is simple. For every element x in the domain, there must be a corresponding output fx in the range. But here is the most important part, the key condition. For every element in the domain, there must be a uniquely defined output. That means no input can have two different outputs. Let's determine if the following mapping is a function. Suppose we have a domain D, 1, 2, 3 and range 2, 4, 6. We define our mapping as fx equal to 2x. So we substitute the input into the calculation, then we get the output. Since every single element in the domain 1, 2 and 3 each gave us exactly one unique result, this mapping passed the test. Therefore, we can confidently say this is a valid function. How are functions a special case of relations? Think of relations as a huge circle. A relation just pair numbers together with absolutely no rules. A function is a smaller, strict circle inside relations. To be a function, a relation must follow one golden rule. Each input can have exactly one output. Look at the example in the box. The first set has 1a in a bracket and 1b in a bracket. This is just a relation because the input 1 splits into two different outputs. The second set gives every input its own unique partner, so it qualifies as a function. In short, all functions are relations, but only the relations that guarantee a unique output for every input get to be called functions. Now, let's talk about the types of relation, which are defined by their properties. The 4 main properties we use to classify relations are reflexive, symmetric, antisymmetric, and transitive. First, reflexive. This means every element must be related to itself. For every element x in set S, the pair x in the bracket must be in the relation. So 1 must relate to 1, 2 to 2, and 3 to 3. Second, symmetric. If the ordered pair x, y in the bracket belongs to R, then the ordered pair y, x in the bracket also belongs to R. So if we have 1, 2, we must also have 2, 1. Antisymmetric. This is the opposite of symmetric in a way. It says if x relates to y and y relates to x, then x and y must be the exact same element. This means for two different elements, you cannot have arrows going both ways, or x must equal y. And fourth, transitive. if X is related to Y and Y is related to Z, then X is related to Z. Let's move on to the calculation part. Let our set S equal to 1 to 3 and let our relation R equal to 1, 1, 2, 2, 3, 3 and 1, 2. First, we test reflexive. We check if every element has a self-loop. So 1, 1 is in R, same goes to 2, 2 and 3, 3. All three are present, so this relation is reflexive. Second, we test symmetric. We check if every pair has it reversed. We have 1, 2 in R, but it's 2, 1 in R. No, it's missing. Since we found one missing reverse, the whole relation fails. So this relation is not symmetric. Third, we test anti-symmetric. We check if there are any opposite pairs for different elements. We have 1, 1, 2, 2 and 3, 3 in a bracket. These are self-loops and they are fine because 1 equal to 1, 2 equal to 2 and 3 equal to 3. Do we have 1, 2 and 2, 1 together? No, we only have 1, 2. Since there are no opposite pairs for distinct elements, this relation is anti-symmetric. Fourth, we test transitive. We need to check every path where the end of one match the start of another. We have 1, 2 and 2, 2 in a bracket. The rule says if 1 maps to 2 and 2 goes to 2, then we need 1 goes to 2. And yes, 1, 2 in the bracket is in R. There are no other chains like 2, 3 or 3 something, so there is nothing else to check. Therefore, this relation is transitive. Since our relation failed at the symmetric test, this is not an equivalence relation even though it passed the other three. Let's discuss the type of functions. In discrete mathematics, we classify functions into three main types based on how they map input to outputs: injective, surjective, and bijective. First, injective or one-to-one. This means each output has at most one input. In other words, no two different inputs map to the same output. The rule is if FA in a bracket equals to FB in a bracket, then A must equal to B. Second, surjective or onto. This means every element in the range is used as an output. The rule is for every y in the range, there exists some x in the domain such that fx in a bracket equal to y. Third, bijective. This is simply a function that is both injective and surjective. It is a perfect one-to-one mapping where every input maps to a unique output and every output is used. This is an example of an injective function, also known as one-to-one function. In this mapping, 1 maps to A, 2 maps to B, 3 maps to D, and 4 maps to E. Notice that no two elements in the domain map to the same element in the codomain. Although C is not mapped, this is still injective because each codomain element is mapped by at most one domain element. Next is the surjective function, also called an onto function. Here, every element in the codomain has at least one arrow pointing to it. For example, X is mapped by more than one domain element, Y is mapped by one element, and Z is also mapped by at least one element. Since every element in the codomain is covered, the function is surjective. Finally, this is a bijective function. A bijective function is both injective and surjective. Each domain element maps to exactly one unique codomain element, and every codomain element is mapped exactly once. Therefore, the function is bijective. Understanding these concepts helps computer scientists design efficient systems, avoid errors, and build the technology we rely on every day. In conclusion, relations and functions are fundamental concepts that power modern computer science. Relations model connections between data. They are the backbone of database tables, social networks, and search engines. where multiple entries can link to the same value. Functions enforce strict one-to-one mappings. They are essential for deterministic programming, primary key lookup in databases, compiler symbol tables, and cryptographic algorithms, where each input must produce a unique and predictable output.